Okay, for this next question, we're going to be looking at some key terms. We're going to start with these first five, and we're going to start with colour depth. We have a representation of colour depth, and as you can see, we have 2 to the 1, which would give us 2 colours, 2 to the 2, which would give us 4 colours, 2 to the 3 would give us 8 colours, 2 to the 4, 16, so as you can see, it's doubling every time. Well, what does that mean? For example, the first one bit of colour equals 2 colours. Well, if I put some bits down here, 1, 2, 4, 8, so we've got 4 bits. Okay, 4 bits. So for example, the first one, 2 to the 1, is either going to be a 0 or a 1, i.e. 2 colours. But if I look at 2-bit, this one up here, I have the possibility of 0, 0, 0, 1, 1, 0, 1, 1. So possible of 4 different colour combinations, as you can see here. Now if I go on to the next one, so this is 2-bit, 1 bit. Okay, if I look at 3 bits, I can go 0, 0, 0, 0, 1. And then I have got to find another 4 different combinations. So for example, I can go 1, 0, 0, 1, 0, 1, 1, 1, 0, and then finally 1, 1, 1. So it gives me 1, 2, 3, 4, 5, 6, 7, 8 possibilities. If I move on to 4 bits, as you can see here, it gives me 16, right down to 8 bits, which we're familiar with, which would give us 256. 24-bit gives us a maximum of over 16 million colours. So the bit depth is basically the number of colours we can represent using bits. So to answer the question, the colour depth is the number of possible colours of a group of pixels based on the bit depth. Okay, the next one, we have ASCII code and extended ASCII code. Okay, so if I bring in the first table, this is showing ASCII code. Now ASCII code is, although I've cropped it off a little bit, is the first 128 characters on a keyboard. If I go down, we've got a backspace key, which is number 8, shift key, escape key, so on and so forth. As you see here, escape key would be represented by the number 27. Obviously, as we go further down, we've got things like the plus sign being 43, and then letters, letter R, represented in either normal decimal or in hexadecimal. So all the different keys on the keyboard are represented using ASCII code. Now we can go a step further where we have something called extended ASCII. I'll put this over the top, and this, as you can see, has a lot more characters, and this goes up to a possible 256, so a lot more symbols. Some familiar ones, 171 is the half, the greater than or equal to, positive or negative signs as well. Move those two out of the way. The next question is Unicode. Now Unicode was developed, as you can see here, Unicode was developed to represent all the different language systems of the world. But what it also includes, which is ever increasing, is these things, emojis. Now Unicode can hold a lot more characters than ASCII or extended ASCII. In fact, we're now to version 14 of Unicode, and the standard number is 144,697 different characters. So as more and more emojis are created, obviously they can take up one of those slots in that particular system. So there we go, 3 different systems to look at different text and different things we can type in to get things to appear on the screen from our keyboard. Okay, let's bring these 2 images in. First of all, we'll start with the big image here. The sampling rate is basically the number of samples taken per second. So if you can see here, we've got on the left-hand side, a very low, sample rate. But as this increases, here's a higher sample rate, the sound quality is improved massively. Why is that? Well, if I show you on this one, If we base it on this, look, you can see that it's following, we're trying to get it to follow the curve as closely as possible. So the more samples that are taken, the closer it is to the curve, and the better the quality in terms of the music. So the higher the sample rate, the better the quality. Okay, that is a sample rate, the number of sound samples taken per second. Okay, what is a bitmap image? Well, a bitmap image is basically an image that's made up of pixels. And we can see here that it's made up of lots and lots of these tiny squares of colour. Obviously, the more pixels per inch, or pixels per centimetre, then the higher the quality image. This is a bitmap image. Okay, so that's the first 5 explained. If I move on to part 2, a colour image is made up of red, green and blue colour combinations. 8 bits are used to represent each of the colour combinations. Well, again, I'm going to use a diagram. So here we go. If it's 8-bit, how many variations of red can we have? Well, we can have 256. How many variations of green in terms of 8-bit? Obviously, again, 256, and blue, the same 256. If we multiply all of those together, then we get a colour combination of 16,777,216. If I bring this, we can see that 8 bits, 2 to the 8, equals 256 colours. So, hence, we have 256 multiplied by 256 multiplied by 256. Okay, and just to answer the final thing, describe the effect of increasing resolution and sampling rate on the size of a file being stored on a computer. If we increase the resolution or we increase the sample rate on the size of a file, well, obviously, in terms of images, it's going to increase the size, and in terms of sound, it's going to increase the size. The higher the quality, the more space it's going to take up, the more space is going to be needed to store that file. Okay, so that answers all of those 3 questions. I hope that's helped. Thank you very much indeed, and I will see you for the final video in this series. Thank you very much indeed.